All right, so today we're going to be doing the last challenge of this year, day 25. The first part of today's challenge is that we get some input, which is either keys or locks. And we can imagine this as different types of pins that have different heights. And we have to see sort of if the keys will match with the locks. If we see these hashtags, if they start at the top and they sort of point downwards with each different pin, it means that it's a lock. If they point upwards like this one, it means that it's a key. And they're sort of random, so we have to figure out if it's a key or a lock ourselves. And what the task is to be able to see how many keys fit in how many locks. So how many combinations can we possibly make with all the keys and all the locks that we get. And there's quite a bit of them. So if we look, there's 1, 2, 3, 4, 5, 6, 7 lines plus the empty space character that we have. So 8 lines, 4,000 divided by 8. That should be like 250 either keys or locks that we get. And then we have to see, okay, how many of them fit with each other and keep them to a counter. So what we can do is we can either sort of manually check, okay, if this is a lock and this is a key, we take this hashtag over here, we plop it in an empty space here, take this hashtag here, put it in the dot, and so on and so forth. And if we get to a point where this hashtag does not fit, because we're not overriding another dot, we're overriding another hashtag, then it means that they overlap somewhere, so actually they don't fit together. They don't have to fit together perfectly, so there can be gaps. So if we have the lock and the key, we can have a bunch of gaps everywhere. There's no problem, it doesn't have to be perfect. But if it overlaps, then we know that it's not going to fit at all. So then we have to reject this one, for example. So we can either do that manually, or there's another approach, which they're giving us an example of, in which we just make a sort of a height map. So this pin's height map would be 0, 5, 3, 4, 3. So there's 0 pins over here, there's 5 pins over here. If we count them excluding this one, because this is just the base, it doesn't really matter if you exclude the base or not, the math is still going to be the same. But they excluded the base, and this one would be 5, 0, 2, 1, 3, and they counted from bottom up, excluding the base as well. So 5 over here, 0 over here, 2, 1, and 3. So once we have the key unlock, we can sort of see how many combinations. If there were only 2 different locks and only 3 different keys, then there is 6 combinations that we have to check in this case, and apparently there's only 3 of them that fit, so that's the answer that we would give them. But in our case, that's not the answer. The answer is a lot bigger. So to begin to solve the problem, we get the input file and we read it by using with open and then the file name, and I'm storing it inside here. So we read it as a file, we get all of the different lines, and the first thing that we have to do is to parse the data, because it's not that every line is a lock, it's that several lines are a lock or a key, and we can split them where we can see 2 new line characters, because there is a new line character here and another one here at this empty space. So if we split them, then it makes our job a little bit easier. So this is what we've done here in parse schematics, to be able to get all of the keys and all of the locks. So if we look at the function, we get all of the different sections by splitting the data with the \n/n. And then for every section in the sections, so meaning we have a specific section, meaning this one. So for every row now in here, we are going to do something special to it. And what it is to just find out, is it a lock or is it a key? And we do that by seeing, okay, are all of the hashtags in a column, in a row, either at place 0 or at place -1. So all the way at the top or all the way at the bottom. And in this case, this one would be a key, the first one. So let's see if we can slowly go over here, and if we can skip through all of this for loop where we added to the schematic. So we press play until it goes here, and we can see that the schematic is indeed the first input that we get. And it will look for all of the different characters and see if all of them are equal to the hashtag for every character in the schematic at 0, index 0, meaning that it's going to look at this row. Otherwise, it's going to look at this one at the -1 row, and it's going to append it to the keys, because that's the keys start from the bottom, the locks start from the top. So in this case, it should be going to the bottom one. So it should not be going inside this if statement. But since there's a for loop inside these parentheses, and we have to go several steps for it to go out. and then it's going to check this one. It's going to check all the different hashtags and see if it's indeed true. And once it checks all the different positions, it's going to append it to the key, and it does that. Now we can see that the key at index 0 has this specific key, and when we add more keys, it's going to have another index with another specific key with all of the rows and columns and everything. So this is going to help us in the future to make everything easier to handle. So once we get all of the locks and all of the keys, we want to convert them to lock heights and to key heights. So we send them to this function, schematic key heights, for every lock in the locks and for every key in keys. But since the key is from bottom up and the lock is from top down, we just have to be careful with how we index stuff. So I also sent a second thing into the same function, which is just make sure to do it in reverse, sort of. And by default, we have reverse to false. And that is why you can see here that I call the same function with one variable and I call the same function with two variables here. That is because we have a default value here. So if I make another function, another variable s is equal to 0, then s will be 0 by default. So it doesn't matter if we send it in or not, it's still going to work. But if we do not set it by default, then it's going to complain and it shouldn't work if we actually try to run it. But since we don't use this at all, then there's no point to adding it. I'm just demonstrating. So what we're going to make is a list with all of the different heights. We're going to need the width, and we get that by getting the length of the schematic at 0, so meaning the 0th index, and then all of the different 0th indexes together. Whoops. And it's going to give us a 5. And we could also just say 5 over here, and it will be the same thing. But in case the input is different for you guys, if they're larger or something, then this should be generalized and it will work for every width and height. And then we get the height by just getting the length of the schematic. What we do after is we iterate through all of the different columns in the width and all of the different rows in the height. And we check if it's not reversed, then we know that we can just take the row and the column directly and get the character and see if it is a hashtag. If it is, then we add 1 to the count. So if we can debug this, continue to over here. Can I play it? Yes. No. Remove this one here. Keep playing it, and now we're over here. So we can open the schematic, which is over here. So this is the current schematic that we have, and we will see if it's not reversed, which is not. It is not, because we can see this is the input that we have, which should be maybe the third one over here. And we check the row, which is currently 0, and the column, which is currently 0, and we get the character, which is a hashtag. So all the way in the corner here, it is a hashtag. Then we add 1 to the count. So this means that the way that we're doing it, we're actually counting even this row over here. So this one over here would be 1, 2, 3, 4, 5, not 4, excluding this sort of beginning layer. But it doesn't really matter, because when we check the keys and the locks together, we just make sure that the total limit that it shouldn't go over should be a bit different. So we do this for every different pin, so to say, and we add a total to it, and then we add it to the heights, and we return the heights for every different key or lock that we have. So once we've done that, we have all the key heights and all the lock heights, and the only thing that's remaining is to get max height so that we know what we shouldn't sort of go over, and that is to not go over locks at index 0. So if I take this away and we press play, we can get max height, which in our case is 7, and as we can see, it's 1, 2, 3, 4, 5, 6, 7 that we shouldn't be going over with, which is correct. And then if we go to count fitting pairs, then we will have this function which takes the lock's heights, the key heights, and it tries to pair them together and make sure that it's less than the max height. And to do this, we have to iterate through every lock and through every key, right? So we make a for loop to iterate through all the locks, another for loop inside that to iterate through all the keys, and we initially set fit to true, because if at any point it becomes false, we just directly break it, and then it breaks from this loop, which will continue to the next key, and then eventually the next lock, and so on and so forth. But if we check one by one and we see that for I in the range of length of lock, so for every different pin, if we check that their lengths are not bigger than the max height, then it means that it did work, so it did fit, and the count should be plus equals 1. But if it did not fit, so if it is bigger than max length, then it's going to set fit to false, and it's going to break and restart, and then set the fit to true again, and then keep doing this over and over again. So it will check it for every key and for every lock combined with each other, and every time that it does find a fit, it does count plus 1. And once we do get the result, all we do is print it. So if I stop this real quick and I run it normally without debugging, we can see that our answer is 3397. And that was indeed the correct answer. So for the time complexity, we can make it sort of complicated for ourselves and have n as the total number of schematics, or even more complicated, you can have L and K as locks and keys, but since they're part of the same input, I'm just going to call it n as the total number of different schematics of locks and keys that we have. We have W, which is the number of columns, and H as the number of rows, which we kind of don't need, but it's just good to showcase for the time complexity and space complexity, since technically if the input were to be 100 by 100 and the keys and locks were really huge, then of course it would take a lot longer to iterate through them and to be able to store them into a map and to be able to process them. So parsing the input, it would be n times the height, converting them into heights would be n, so how many there are, and then width times height, since we have to iterate through the entire grid to be able to do that. Counting the fitting pairs would be n squared times w, and this is because we have to go through every row and through every key and through every lock. So if we go n times for the first lock, and then n times for the second lock, and n times for the third lock, and so on and so forth, then eventually it will be n squared. And technically it can't be n squared, it should be less, because n is locks plus keys, so maybe it should be divided by 2, but I've just left it as n squared. So if we add everything together, this is what it becomes, but we don't need everything actually, we just keep the most significant thing, so we can say that it's n squared. And we could make it slightly more efficient by just sorting all the keys and locks and sort of seeing how many pins they have to begin with, and if we should even compare them, and that would take a little bit of time, but it's just a lot of work for not that much efficiency, and as we can see it runs in about 1 second, 2 seconds, so it's not too bad. And for the space complexity, it's O of n, which is not too bad, but we also have to keep all the rows and columns and the entire input, so however big the input is how much we actually have to store in the memory. And that was part 1, and for part 2 there is actually nothing, as it is in every year of Advent of Code. The last day does not have a part 2. The only thing that you have to do is to read the lore, see what's going on, and then you just deliver the Chronicle, which you can do if you've managed to complete all the stars. So I haven't clicked it yet, and let's see what happens. This is my first year doing these challenges, so I actually don't know. It seems that we just get the point. So now we have 50 stars, and if you did not have 49 before, so if you did not complete all the different challenges, then you can't click it and get the last point. But you can look at the different solutions that we've made over the days. I will leave the GitHub in the description so that you can look at the different solutions that we've made and get some inspirations from that. And there's some nice animations. If we look at the calendar over here, you can see that it's a bit animated, which is cool. So that was Advent of Code 2024. If you guys want to join the leaderboard still, I will leave the code in the description. Thank you for watching. Holidays are almost over, but Happy New Year soon. And see you guys in 2025 Advent of Code.